Okay, Dr. Lane, this problem I thought was really interesting, and it really does show how potential energy is great using a spring dart loaded in a gun. And anyways, the question goes, in a dart gun, a spring with 400 N over M is compressed to by 8 centimeters when the dart mass M equals 20 grams is loaded. What is the muzzle speed of the dart when the spring is released? And it's telling us to ignore the friction. So, so, well, the elastic energy initially is stored in this spring. It actually is converted into kinetic energy as the dart expands. So there's no change in the gravitational potential energy since the motion of the dart is going to be horizontal. So the vertical and normal force do not work because they are perpendicular to the displacement of the dart. So the spring pushes the dart to the right until it reaches its relaxed length right here, which, pushes this. And we can assume that the spring cannot pull the dart to the left, because if it did, it would just stick it together and it would ruin it, shooting out in this motion. Anyways, so the dart loses contact with the spring when it's at its relaxed point. And anyways, so for this, I chose the origin at the relaxed position. So that gives us the x final equals 0 centimeters. And then using the x-axis, I can show you that the initial x is actually negative 8 centimeters because it starts from rest. So the initial velocity is actually going to be 0. So what we need to find is we got to find this final velocity right here. So I can show you what we have is we know that the final velocity of x is 0. The initial velocity, the initial x is negative 8 centimeters, and the initial velocity is 0. We need to find the velocity, the final velocity. So since we're ignoring friction, no work is done by the non-conservative forces. So we get to use this using this formula. So K sub I plus U sub I equal to K sub F plus U sub F. And we can ignore the gravitational potential energy because it doesn't change in this problem. So we put in this equation for the elastic potential energy in the spring. So we get 1/2 mvi sub I squared plus 1/2 k sub I squared is equal to 1/2 mv sub f squared. That shouldn't be there. It should be right here. Sub I squared. And then we do plus 1/2, and it's kx sub I squared. And then it's 0 plus 1/2 kx sub I squared. It equals 1/2 mvf sub I f sub f squared plus 0. So then we use the final velocity. So we get the formula Vf, and it equals square root of k over x times x sub I, which equals to, I plugged in my values for this, and I get 11 meters per second for my final velocity.